Hello, this is Module 10, which is air currents. So basically, there's four different ways that air circulates. So circulating around the globe, we're talking about. So one is density. So less dense air rises, denser air sinks. And this is caused by heating. So warm air is less dense. As the molecules spread out, they become less dense and they rise. And then as air cools, the molecules condense and it sinks. And so that's one way is just simply a convection current, so density current. Another way is water vapor. And so water vapor, if it's holding as well as air temperature drops, it can't hold as much water. And so that's why we tend to see as air temperatures drop, we tend to see fog forming or we tend to see clouds forming. And that's just because it can't hold as much water. And then in the summertime around here, think about as air temperatures heat up, it gets drier out, and so that also has to do with water vapor. All right, so if we look at this diagram, this graph, what it's showing adiabatic cooling. And so basically what that is, and that's what I talked about as far as water vapor goes. But as temperature rises, the saturation point also increases. So as temperature goes from -20, let's say, to 50 degrees Celsius, it's as we go along this curve, notice how the saturation point goes up. So saturation point means when the air is fully saturated, which is fully full of water. So as the temperature rises, it's that saturation point goes up as well. So it can hold more and more water. And as the temperature drops, if we go the opposite way, as temperature drops, it can hold less water. So let's say that it's holding a certain amount of water, and as the temperature drops, it can't hold as much. So when it gets to that saturation point, that's when we get dew forming. That's when we get cloud formation as that temperature drops. And that's why in the morning you see dew, like on your car, for example, is because the temperature dropped and that moisture that was in the air was colder, so it can't hold as much. So instead of being 60% humid, it's now 100% humid because the temperature dropped. And then you get that dew formation on the grass or on your car. All right, and then a third reason that air circulates is, like I said, adiabatic cooling and adiabatic heating. So once again, you've got similar to density, but as air rises in the atmosphere, it expands and moves out, so it's spread out more. So that's cooling. There's not as much heat that's trapped in there. And then as it sinks, that heating, or if the sun's hitting it, that heating causes that sinking. And so it's this huge circulation, which I'll show you in a minute. And then the fourth one is latent heat. So you might have heard of this or talked about this in chemistry. But when water vapor in the atmosphere condenses, it releases heat. So that would be that latent heat release as temperatures cool. All right. So what all this affects is the global circulation of air, which is really important for climate. It's really important for all of our biomes and ecosystems and weather. So basically, all of those four things drive all of this that's on Earth, and that's a whole bunch of convection currents. So what it results in is just this huge convection of air. All the way from the surface of the earth to the upper atmosphere and all the way from the equator to the poles. So it's this huge circulation. Um, and it also drives different climates, especially if we think about climates, how they differ on the coast versus how climates differ in deserts, for example. So these convection currents, if we've got this just small convection current here. So here we've got cold, dry air as it rises, it expands and spreads out, and so that cools, and so it sinks. So we've got this adiabatic heating as it drops to the surface of the earth. The earth is warmer on the surface, and so it's heating, and it picks up moisture, so it picks up maybe evaporation. And then as it rises, it cools. And remember, when I said it cools, it can't hold as much moisture. So as it heats up, it's absorbing that evaporation. But then as it rises back up, it's releasing that heat energy. And so that heat energy is in the form of clouds, water vapor. So that's why in the mountains often we get thunderstorms or clouds forming in the mountains, and that's because that air is rising and can't hold as much water, and so that precipitates out, and then you get that whole circulation occurring again. And so that would be our convection currents. All right, and then there's these cells on Earth, and so we've got Ferrel and Hadley cells and polar cells. There's three types of cells, and we're talking about in the upper parts of the atmosphere. So we're talking about this atmospheric circulation. So at the equator, we have, and this is really important. So definitely understand these cells. Extremely important. If you had Earth Science, you probably talked about them in Earth Science. If you didn't, then you'll still need to know them. But so ITCZ, this occurs near the equator, so it's not necessarily on the equator. But as the Earth is tilted, we get our different seasons. And so in the summer versus the winter, this band, this ITCZ band, it stands for Intertropical Convergence Zone. So it's where the two hemispheres join, where they converge, and we get this difference in weather. So this is where we often see monsoons, and for a reason I'll talk about in a minute. But this band, as it moves from summer to winter, the band moves along with it because we get unequal heating there at the equator. So you get this moisture rising, right? You get this evaporation occurring. And so you can see as it rises, that adiabatic cooling is causing it to form clouds. So we get this moist tropical region. And then as it rises, that air dries out because it spreads out. And now and it loses its moisture as it precipitates. And then it's sinking. And so as it sinks, it's heating up. And when air sinks, we get our desert region. So notice how everywhere where we've got the air sinking creates this hot, dry desert. Well, because the Earth is tilted, and this is caused by the heating of the Earth. So if the heating of the Earth changes because the Earth is tilted, and we get sometimes the sun pointing below the equator more directly, sometimes it's above the equator. Just depends on the season and how the Earth is facing the sun. So this moves. So we've got this hot, moist tropical area, but in the summertime, this area can move here. And then in the wintertime, this area can move here. So it kind of fluctuates back and forth like this. And so that creates this intense rain. Think about India, for example. They have this intense rain in the monsoonal season, and then this very hot, dry season as well. And so that's because this moves. So this band, this ITCZ band, will go from at the equator up to about 30 degrees north and about 30 degrees south. So as it fluctuates as the Earth is tilted towards the sun, and as the Earth goes around the sun. So that will be our monsoon season. So when we have this raining season, that would be our monsoon, and then we've got the hot, dry region when it's not over that. So that's a Hadley cell, and that occurs at the equator. So you've got this cell occurring here. This is a big convection cell, and then you've got this big convection cell here. So at the equator, right here, that would be our Hadley cells. All right, and then what creates this cell, this movement, is the Coriolis effect. So the Coriolis effect is the Earth spinning, so it rotates on its axis, and so when it does that, it causes deflection. So think about if you've ever been like on a merry-go-round or something, and if you go to throw a ball at somebody and you're on the merry-go-round, the ball is going to look like it curves off to the side, when in reality it went straight. So here's that example. If a ball is thrown from the North Pole to the equator, it's going to be thrown in a straight path. You can't, I mean, unless you're throwing a curveball or something, but you're throwing in a straight path. Well, what happens is the Earth is rotating under, and the ball is not attached, just like the air is not attached to the Earth. And so that air or ball is deflected. So notice how it's deflected here to the left as the Earth is rotating under it. So the air does the same stuff. So as the air moves, it's sinking at the pole because it's cold, and it's moving along towards the equator, wanting to anyways. And so as it does that, though, the Earth is spinning under it. So as it spins, it causes this deflection. And so that's basically the Coriolis effect. So it's being deflected as the Earth spins. And so notice here, if we look at the side view, the Earth is rotating counterclockwise. So we've got air rising here, and it's being deflected. So it's wanting to rise up towards the North Pole, but it's being deflected because the Earth is spinning. And then same thing here. So it creates this big kind of circular pattern. And so that would be another cell. So we've got this Hadley cell here, but then we've also got another cell here and another cell here, which we'll talk about. And the same thing is occurring down here, but notice how it looks like it's going in the opposite direction. So this circulation would be counterclockwise. The circulation in the northern hemisphere is clockwise. And this is also why we get hurricanes spinning in certain directions. So hurricanes in the northern hemisphere always spin counterclockwise. Hurricanes in the southern hemisphere always spin clockwise. They spin opposite of this. And we'll talk a little bit about that with weather. That was more earth science. We will talk a little bit about that. But basically, just know that in the northern hemisphere, it's a clockwise circulation, and the southern hemisphere is counterclockwise. And then this is important. So Coriolis effect, just know that that's a deflection because the Earth is spinning under. All right, so here's a little video about those three cells. So I mentioned the Hadley cell at the equator. We've also got Ferrel cells, and we've also got polar cells. So you start at the equator and you have the Hadley, and then you've got Ferrel, kind of where we are, Ferrel cells. And then polar cells would be towards the North and the South Pole.
The last video showed that different parts of the Earth heat up differently, with the equator receiving more radiative heat from the sun than the poles. And the purpose of global circulation is to redistribute this heat. If the Earth did not rotate and was a simple landmass with no oceans, we would have a single circulatory cell in each hemisphere, where hotter air would rise at the equator and flow toward the poles. The air would sink as it cools and then return towards the equator. But the unequal distribution of land and ocean and the speed of the Earth's rotation make this circulation system more complicated, giving us a three-cell pattern which exists in both the northern and southern hemispheres. The largest cells are the Hadley cells. At the equator, the warmer, less dense air rises. It rises to a height of about 18 kilometers and spreads out underneath the tropopause. The tropopause acts as a lid to the lowest part of our atmosphere, which contains all of our weather. The warm air spreads out towards the poles, gradually cooling and sinking as it moves, before descending to the surface and flowing back to the equator. The smallest cells are the polar cells. Cold, dense air descending in the polar regions flows at low levels to about 60 to 70 degrees north or south. As the air leaves the polar regions, it starts to warm and rise, returning to the poles at high levels. Between the Hadley and polar cells are the Ferrel cells. Unlike the other cells, the Ferrel cells are not driven by temperature. These cells flow in the opposite direction to the Hadley and polar cells, acting like a gear. These circulating cells not only transport heat from the equator to the poles, but also result in semi-permanent areas of high and low pressure due to the rising and descending parts of the circulation cells, giving us our climatic zones. Where air is rising, an area of low pressure is created, so these areas see much more rainfall. This is why the largest areas of rainforest are found near the equator, and why the United Kingdom has a relatively wet climate. Where air is descending, an area of high pressure forms, giving largely clear skies and little rainfall, which leads to the desert regions. But not all deserts are hot. Antarctica sits under the descending branch of the polar cell and is also classed as a desert. With more precipitation falling in the Sahara, Antarctica is the largest and driest desert overall.
It's pretty cool to think that Antarctica is a desert. So desert is classified as basically because of rainfall. And so if you've got less rainfall, then it's a desert. So the cells that they talked about and that circulation pattern is extremely important, especially when we talk about where our biomes are located. So definitely make sure you understand that. And it's all due to the Earth's circulations or the Earth's spinning. So it's pretty amazing how everything's really tied together. I think. All right, so here's that pattern that it was talking about. So we've got this Hadley cell circulation, and we've got the Ferrel cell circulation, and we've got the polar cell circulation. So this is extremely important to understand. So I would definitely try to memorize this or study this. Definitely know this. And it will come in handy, not just because I'm not going to test you. I wouldn't have you necessarily label these. I mean, I might have maybe Ferrel cell or Hadley cell or something like that, but I wouldn't have you draw something like this with arrows. But when we start talking about why different climates are where they are, why ecosystems occur where they are, why certain weather patterns affect different places more so, this is extremely important. So this is basically why all of that occurs and all of those ecosystems are where they are, which is definitely part of environmental science, studying those. So definitely this is very important. So I want you guys to notice where the air is rising. Everywhere where we have air rising, we've got lots of rainfall. Everywhere that air sinks, we've got our desert regions. So exactly why. Rising air, this is where we've got our, wet climate, like think of Washington, Oregon, our desert region right in here. On the other side of the earth, that's where we have the Sahara. And then down here, we've got desert region here. This is where we have our rainforest region, is right in here. And that's exactly why. And here's that ITCZ band. So that band will fluctuate. So the stuff will kind of shift because the earth is not, it's tilted, right? It's not just like it is in this picture. So because it's tilted, sometimes it's tilted. So the southern hemisphere is tilting away from the sun. Sometimes the southern hemisphere is tilting towards the sun. And so that causes this whole thing to kind of shift a little bit. And it only shifts up to 23.5 degrees north and 23.5 degrees south, which are also pretty important bands to remember. So this 23.5, that happens to be the tilt of the earth, is 23.5. But this is the Tropic of Cancer. And this one down here is the Tropic of Capricorn. And so that will be where the sun is directly overhead. It is not directly overhead anywhere south of that or north of that. So in the summer, we'll never see the sun directly ahead of us. We'll see it kind of tilted to one side. And that's because we're above that. So all of that's really important to remember.
The last video showed that our atmospheric circulation is split into 3 cells in each hemisphere: the Hadley cell, Ferrel cell, and polar cell. In this third video in the Global Circulation series, we will look at the winds within these cells and how the rotation of the Earth influences these winds to give us jet streams and prevailing wind patterns. As well as being split into 3 cells, the global circulation pattern is at an angle due to the Earth's rotation. The spin of the Earth induces an apparent motion to the right in the northern hemisphere and to the left in the southern hemisphere. This is the Coriolis effect. The key to the Coriolis effect lies in the fact that the Earth's surface rotates faster at the equator than at the poles. This is because the Earth is wider at the equator, so it has further to travel in one day. The result of this means that as air moves away from the equator, it doesn't move in a straight line relative to the Earth's surface. Instead, it appears to an observer on the ground to move in a slightly curved direction. But there is no physical force causing this deflection, as the atmosphere rotates with the Earth. It is just due to the air flowing from a region that is moving faster to a region that is moving more slowly. To explain this further, imagine an air parcel as a ball. The ball is thrown from the equator towards a point near the North Pole. Even though it moves in a straight line, the ball will appear to an observer on the ground to curve away and land to the right of its target, as the point near the North Pole is moving more slowly and is not caught up. If the ball is now thrown from the North Pole towards a point near the equator, it will again appear to a surface observer to land to the right of its target. But this time it's because the Earth's surface at the equator is moving faster and has moved ahead of the ball. This effect only happens on objects that are in motion. This deflection is a major factor in explaining why winds blow anti-clockwise around low pressure and clockwise around high pressure in the northern hemisphere and vice versa in the southern hemisphere. So when flowing towards the North Pole, air is deflected towards the east, and when travelling southwards back towards the equator, it is deflected westwards. The same overall result occurs in the southern hemisphere. How does this lead to eastwards flowing jet streams and prevailing winds? As air moves away from the equator at the top of the Hadley cells towards higher latitudes, it starts to be deflected by the Coriolis force. Just as a skater spins faster by bringing their arms and legs closer to their bodies, air moving away from the equator speeds up as it gets closer to the Earth's spin axis. This process is known as the conservation of angular momentum. The magnitude of the Coriolis force increases towards the poles. So by the time the air reaches 30 to 40 degrees north or south, it is moving in an eastward direction. This subtropical jet stream occurs high in the atmosphere between 12 to 15 kilometers. It is associated with some of the strongest winds on Earth, reaching over 280 miles per hour at times. As this jet sits between the descending branches of the Hadley and Ferrel cells, there is little associated weather. The polar front jet forms in a different way. This jet sits between the rising branches of the polar and Ferrel cells. It marks the boundary between cold polar air and warm tropical air, known as the polar front. The polar front jet occurs at a height of 11 to 13 kilometers and is primarily the result of the temperature contrast across the polar front. The stronger the temperature contrast across the front, the stronger the jet. So it follows that the polar front jet is stronger in the winter than the summer. Waves or ripples along the jet stream can cause Atlantic depressions to deepen explosively as they are steered towards the UK. Winds at the surface are also subject to deflection from the Coriolis force. The surface flow of the Hadley cells form the persistent trade winds. As air flows towards the equator, it is deflected towards the west in both hemispheres, forming the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. The persistence of these winds allowed sailing ships to cross the Atlantic and opened up trade routes between Europe and America, giving them their name. The surface wind in the Ferrel cells would flow from a southerly direction in the northern hemisphere, but the Coriolis effect causes this wind to be deflected to the right, leading to the prevailing westerly and southwesterly winds often experienced over the UK. This setup is not unique to our planet. Jupiter also has circulation cells similar to those on Earth. The day on Jupiter lasts for about 9.5 hours, so it is rotating much more quickly than the Earth. The great size and fast rotation of this planet makes the Coriolis effect very strong. This splits the Jovian atmosphere into many circulation cells in each hemisphere, producing numerous alternating bands of rising and falling air and giving Jupiter a distinctly striped appearance.
All right, so we got just a couple more things to talk about, but rain shadows. So basically, a rain shadow is an area caused by mountains. And so here we've got, think about Eureka, think about our coast. So you've got really wet area on the coast, but then the minute you go up and over those mountains, it becomes very dry, kind of like the Willow Creek area out to basically from the coastal range to Redding, it's much different climate than it is on the coast. And so that's because of a rain shadow. And you get the same thing in Nevada. So think of these as being the Sierra Nevadas. And this is Nevada over here. This is the western part of Tahoe. And so we've got moisture evaporating here. And remember the adiabatic cooling, as air rises, it can't hold as much moisture. So as air rises, it creates this precipitation. And when it gets up and over the mountains, it has lost a lot of its moisture. And then as it sinks, it's heating and it can hold more moisture. So it becomes very dry. So that's a rain shadow. So this is the rain shadow area. And it's also called the windward side. And this would be the leeward side. And so the windward side, where the wind is coming from, is very wet. The leeward side is very dry. So this area here is the rain shadow. And that's also really important, especially when we're talking about little pockets of climate. So this ecosystem is going to be much different than this ecosystem, and it's 100% due to the mountains. So, for example, if we didn't have the coastal range, our climate would be a lot different than it is. It'd be more similar to, it'd be warmer, but it would be more similar to a wetter environment like Eureka. All right, and so here's another example. This is the Sierra Nevadas. So Mount Whitney down in Southern California. We've got this rain occurring on this side of the mountain, so the windward side. And then the leeward side, here we've got Death Valley. So it's pretty extreme as far as the arid rain shadow effect.
Aloha, young people. The rain shadow effect on the Big Island of Hawaii. Rain shadows are dry areas on the back sides of mountains. The downwind side of a mountain, the mountain creates a shadow of dryness. We've got that here on the Big Island. It's the most famous place to study this effect. You can go wet side to dry side of this island in a 60-mile drive and go from Hilo side, which is more than 120 inches of annual precipitation. That's more than 10 feet, by the way, of rain per year, up and over the Saddle Road to the Kona side of the island, which has less than 10 inches of rain a year. That's quite a transition. What is going on here? Here in the Pacific Northwest, we've got the same effect. Western Washington is famous for its rain, but there's a strikingly different landscape on the other side of the Cascades. Washington's the evergreen state, but half of it's everbrown. Okay, you want a rain shadow effect? You need three essential items: an ocean nearby, winds blowing steadily onshore, and a mountain range to block the traveling air mass. Here's how it works. Evaporation on the surface of the ocean creates moist air. Prevailing winds push the wet air inland until it hits the base of the mountains. The air is forced to rise, and as the air lifts, it expands and cools. Cooler air can't hold as much moisture, so clouds form, and it rains a bunch, resulting in a lush green landscape. The now dry air mass crosses the mountains and begins to sink on the leeward side of the range. It compresses and warms, promoting evaporation. Dry air warms 1 degree Celsius per 100 meters of elevation drop. Some of the driest places around the world exist because of the rain shadow effect. There's a rain shadow north of the Himalayas in Asia, a rain shadow west of the Great Dividing Range in Australia, a rain shadow east of the Sierra Nevada mountain range in California, and that rain shadow southwest of Mauna Kea on the Big Island of Hawaii. And here in the Pacific Northwest, we actually have two rain shadows. In winter months at higher elevations, it's not rain. Up here in the Cascades, annual snowfall is measured in tens of feet. The soaking rains on the wet side and deep mountain snows have helped shape our landscape. Sharp mountain peaks, carved by glaciers and huge landslides in the lowlands, like the tragic 2014 Oso slide, where ground saturating rains caused thick glacial deposits from the Ice Age to unexpectedly slide into the river valley below, sweeping homes away. The rain shadow effect has been a great help to geologists in the Pacific Northwest. The Cascades have cast a rain shadow on Washington's channeled scablands, our desert landscape that has yielded so many clues about the Ice Age flood, the Columbia River basalts, and other wonders of our geologic past, just like back in Hawaii. It's all out here to see. Oceans, rocks, and lava, the scenery. Right here for you and me. 2-minute geology.
All right, and that would be it for Module 10. I will see you next time.